Hey everyone, and welcome back for another deep dive. Today we're taking a plunge into the world of chemistry. But not just any chemistry, oh no. We're talking about the kind that makes you the life of the party, with maybe a few safety precautions, of course.
Well, explosions aren't always the best party trick.
Sure. But they're definitely attention-grabbing. And that's what we're diving into today. Alkali metals and their, shall we say, energetic reactions with water, like the kind that might make you say, whoa, science.
It all comes down to those tiny particles, atoms, and their electrons. Those are the real party animals.
Right. We've all heard that alkali metals react with water, and
Yeah.
sometimes things get a bit explosive.
A bit.
But I think it's time we break it down. What's actually happening at the, atomic level when, let's say, a chunk of sodium decides to take a swim in a glass of water?
So picture alkali metals as these incredibly generous, sharers. They've got this one outer electron they're just dying to get rid of.
Dying to get rid of. That sounds dramatic.
It is. And water's got this structure that's perfectly happy to take that electron. It's like a match made in, maybe not heaven if we're talking explosions, but definitely a perfect match in the atomic world.
So it's this, exchange of electrons that sets off the whole shebang.
You got it.
Yeah.
That exchange releases a burst of energy. That's what creates all the heat in those crazy bubbles you see. And sometimes, if things get really wild, it generates enough heat to ignite the hydrogen gas that's also produced in the reaction.
Wait, hold on. Hydrogen gas. Where's that coming from?
Ah, that's the fun part. See, when the alkali metal reacts with water, it doesn't just donate an electron, it actually breaks apart the water molecule itself. And one of the byproducts of that split is, you guessed it, hydrogen gas.
Okay, and I remember from high school chemistry that hydrogen gas isn't exactly known for its chill vibes, right?
Definitely not. It's highly flammable, so you've got this energetic reaction already happening, plus a flammable gas being released. It's basically a recipe for a very exciting chemistry demonstration.
Okay, that makes sense. But one of the factoids you all send in mentioned potassium burning with a purple flame. Why purple? Is there something about potassium that makes it burn that color?
Absolutely. It all has to do with the energy released during the reaction. When potassium's electrons get all excited, they release that energy as light. And the specific wavelength of that light happens to be in the purple part of the spectrum.
So each element has its own light show, basically. That's so cool.
It is. And chemists actually use this principle in what's called a flame test to identify different elements. They basically just set things on fire and see what color the flame is.
Wow, that's a pretty straightforward approach.
Okay.
Okay, so we've got this electron exchange, water splitting, flammable gas, and colorful flames. But you also mentioned that not all alkali metals are created equal when it comes to, let's say, their enthusiasm for reacting with water. What makes some more reactive than others?
That's where our old friend, the periodic table, comes in. The further down you go in the alkali metal group, the more reactive they become. Take cesium, for instance. It's at the bottom of the group, and it's infamous for its very enthusiastic reaction with water. Let's just say it's not one you want to try at home.
Cesium, the king of the alkali metal party.
Yeah.
But why is that? Why does reactivity increase as you go down the group?
It all boils down to how tightly those outer electrons are held. As you move down the group, the outermost electron is further and further away from the nucleus, making it easier to lose. And the easier it is to lose, the more vigorous the reaction with water becomes.
So it's all about location, 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 even on an atomic scale. Okay, so that makes sense. But here's my question. If these alkali metals are so reactive, especially with something as ubiquitous as water, how on earth do we handle them safely? Storing something that could explode with a drop of water sounds like, well, a recipe for disaster.
That's where those shielding techniques come into play. One of the factoids you guys sent in mentioned storing them in mineral oil. There's a very good reason for that.
Right. So keeping them submerged in oil. But why oil? What's so special about it?
Well, mineral oil acts as a barrier, preventing contact with both air and moisture. And those are the two things that could set off those unwanted and potentially dangerous reactions. It's like giving those overly enthusiastic electron donors a time out.
So it's all about isolation.
Yeah.
Keeping those reactive elements on lockdown until we need them.
Exactly. And of course, when scientists work with these elements in the lab, they have a whole arsenal of other safety protocols in place. Specially designed labs, airtight containers, and of course, highly trained professionals who know exactly what they're doing. It's a high security operation, but instead of guarding valuables, they're guarding against, let's just say, unintended fireworks.
I can only imagine. This is all incredible. So we've learned that alkali metals react with water because of their atomic structure, releasing flammable hydrogen gas and creating those impressive and sometimes explosive reactions. And we've seen how different alkali metals exhibit varying levels of reactivity with cesium, let's just say taking the gold medal for explosiveness. But before we move on, I have a question for you.
Go for it. I love a good question.
So if this reactivity is all about losing that outer electron, are there other elements out there that might exhibit similar, explosive tendencies when they encounter water? It feels like we've only just scratched the surface of this explosive world of chemistry.
That's a fantastic question, and the answer is yes. There's a whole other group of elements that, while maybe not quite as dramatic as the alkali metals, can still put on quite a show when they come in contact with water.
More elements that go boom in water. This is even better than I imagined. Tell me more.
Well, let's move over a column on the periodic table and meet the alkaline earth metals. They've got their own stories to tell when it comes to water and reactivity.
Okay, alkaline earth metals. I am intrigued. Lead the way.
Welcome back. We're continuing our exploration into the fascinating world of reactive elements. It's amazing to think about all the activity going on at such a tiny scale.
It really is. Last time we were talking about those super reactive alkaline metals and their, let's just say, dramatic reactions with water. You were about to introduce us to their, I guess, slightly less dramatic neighbors on the periodic table, the alkaline earth metals.
Yes. Alkaline earth metals are really interesting. They also have a tendency to lose those outer electrons, but instead of losing just one, they tend to lose two.
Two, so double the fireworks.
Not exactly. While it might seem like that would mean an even bigger reaction, they actually hold on to those outer electrons a bit tighter than the alkali metals do.
So maybe less kaboom and more like, I don't know, a sparkler.
I like that analogy. The reactions with water still release heat, but they're generally less vigorous, let's say.
Got it. Less intense, but still interesting. Do you have a favorite example of an alkaline earth metal reacting with water?
Let's take calcium, for instance. When calcium reacts with water, it forms calcium hydroxide and, you guessed it, hydrogen gas.
Wait a minute, hydrogen gas again? That seems to be a recurring character in our reactive element saga. So even though the reaction is milder, we still need to be aware of that flammability factor, right?
Absolutely. Hydrogen gas always adds that extra bit of excitement to the mix.
I'm starting to think we need to do a whole deep dive on hydrogen sometime. But for now, are there any other elements we should add to our list of, let's call them water reactive elements?
Well, there's one more group that deserves an honorable mention on our list. The halogens.
Halogens. Now, those I remember. Fluorine, chlorine, bromine. We're talking swimming pool chemicals here.
Exactly.
But I don't recall them being particularly explosive, at least not in my swimming pool.
You're right. They don't typically react with water in the same way those alkali metals do, but they are incredibly reactive in their own right, just in a different way.
Okay, so if they're not exploding, what are they doing? What's the danger, so to speak, with halogens in water?
So instead of losing electrons like the metals we've been discussing, halogens are actually all about gaining an electron. They're kind of like the opposite of the alkali metals, always looking to fill that one empty space in their outer electron shell.
So they're like the collectors of the periodic table, always on the hunt for that missing piece to complete their set.
Exactly. And when they react with water, they can form acidic solutions.
Acidic solutions. Okay, so maybe not kaboom, but still not something I'd want to be splashing around in. Any examples come to mind?
Well, let's take chlorine, the one you mentioned earlier about swimming pools. When chlorine reacts with water, it forms hypochlorous acid, which is what helps keep our pools clean and safe for swimming.
So the same element that can form a, potentially harmful acid is also what's keeping our pool water safe.
That's fascinating. It is, and it just goes to show that reactivity isn't inherently good or bad. It all depends on the context and how we understand and utilize it. In fact, this very reactivity is what drives so many essential processes in our world, from the biological reactions within us to those huge industrial processes that make so many of the things we use every day.
Right, so it's not about fearing reactivity, but understanding it, respecting it, and harnessing its power for, well, good, hopefully. Speaking of which, earlier you said that it's not just about how many electrons an element has or wants that determines how reactive it is, right? There are other factors too.
Absolutely. The size of the atom and how strong the bonds are that it forms, those also play a role.
So it's a multivariable equation. It's not just electron behavior.
Yeah.
It's this whole collection of properties that determine reactivity.
Precisely. Chemistry is rarely simple or straightforward. There are always multiple factors at play.
This is making me wonder, are there any elements that are just completely chill? Elements that don't really react with much of anything, the wallflowers of the periodic table?
You're talking about the noble gases. They're content with their electron arrangements, and they don't really have the urge to react with other elements.
Okay, tell me more about these noble gases. Why are they so noble?
Well, unlike the other elements we've talked about, they're not looking to gain or lose any electrons. They've already got a full outer shell of electrons, which makes them very stable.
Ah, so they've already achieved that perfect electron balance. They're not needy, they're just happy being them.
Exactly. And this lack of reactivity actually makes them quite useful. Think about helium, for example. It's used in balloons because, unlike hydrogen, which we know is flammable, helium is so unreactive that it won't combust.
So the noble gases are useful because they're not reactive. That's pretty cool.
Yeah.
We've got the electron givers, the electron takers, and the I'm good with what I've got elements.
Mhm.
It's amazing how diverse the periodic table is.
It is. Each element, whether it's reactive or not, has its own unique role to play.
Well, we've covered a lot of ground today. From the alkali metals' explosive tendencies to the halogens' acidic side and the noble gases' I'm good attitude. But, as we've been hinting at, there's a whole other side to this world of chemical reactions, right? One that's a little less dramatic, but no less important.
You're right. There's a whole universe of reactions happening all around us all the time that are quietly shaping the world as we know it.
That sounds like a perfect topic for part 3. I'm ready to dive into those quieter reactions and discover what wonders they hold.
Sounds good to me. Join us next time as we explore the fascinating world of chemical reactions beyond explosions.
Welcome back, everyone. We've been on quite a chemistry adventure, haven't we? From those explosive alkali metals to the halogens and their acidic personalities, and even those noble gases just chilling out, content with their electrons. But as we've been hinting, there's a whole other side to the world of chemical reactions.
Absolutely. It's easy to get caught up in the drama of those big explosive reactions, but the truth is, most chemical reactions are happening all around us, all the time, in a much quieter, more subtle way. And they're just as important, if not more so.
That's a great point. I'm ready for a change of pace. Can you give me an example of one of these quieter reactions that's having a big impact?
Let's talk about rust. Now, I know it doesn't exactly sound as thrilling as an alkali metal taking a dip in a water bath, but rust formation is a prime example of a slow, gradual chemical reaction that's actually having a huge impact on our world.
Rust. You mean that reddish-brown stuff that seems to appear on anything metal if you leave it outside long enough? I have to admit, I never really thought of it as a chemical reaction, more like, well, just a fact of life.
It is a fact of life, that's for sure. But it's also a chemical reaction. At its heart, rust formation is what we call an oxidation reaction. Basically, it's iron reacting with oxygen in the presence of water. And while it might seem insignificant on a small scale, trust me, the impact of rust is anything but small.
Okay, so when I see that rusty old swing set at the park, it's really a slow-motion chemical reaction in action. That's kind of cool, actually.
It is, and when you think about it on a larger scale, the impact is pretty significant. Rust can weaken structures like bridges and pipelines, compromise the integrity of all sorts of materials, and even damage historical artifacts. It's a constant battle against the elements, really.
Wow, that puts things in perspective. It's like slow and steady wins the race, or in this case, causes the most damage. So we've got these big explosive reactions and then these slow, steady ones. But it makes me wonder, what about the reactions happening inside of us? Those have to be pretty important too, right?
You are so right. In fact, every single second, there are trillions of chemical reactions taking place inside your body. They're what allow you to breathe, think, move, digest that delicious lunch you had, basically everything.
Trillions.
Wow.
And we just go about our day completely unaware of this microscopic world buzzing away inside of us. It's mind-blowing.
It really is. And one of the most important types of reactions happening inside of you are what we call enzyme-catalyzed reactions.
Enzymes, those are those protein molecules that, like, speed up chemical reactions, right?
Yeah.
I remember learning about them in biology class, but I never really connected them to chemistry before.
It's a perfect example of how chemistry and biology are completely intertwined. Enzymes are like little molecular machines, each with a specific task to perform. And they're essential for virtually every process in our bodies. They help break down food, build new cells, get rid of toxins. The list goes on and on.
Wow, it's like our bodies are these incredibly complex factories with all these tiny little workers doing their jobs.
That's a great analogy. It's a beautifully orchestrated system, really. And it's all thanks to the magic of chemistry.
This has been such an eye-opening conversation. We've gone from explosions to rust to the microscopic world inside our own bodies. I have to say, I'm starting to appreciate just how vast and important chemistry is. It's not just something that happens in a lab, it's happening everywhere, all the time.
You got it. Chemistry is the foundation of, well, pretty much everything. And the more we understand about how it works, the better equipped we are to solve problems, create new things, and make the world a better place.
That's a great point. Well, I think it's safe to say our deep dive into the world of chemical reactions has been a resounding success. Who knew there was so much to discover?
It's been a pleasure exploring all of this with you. And remember, folks, chemistry isn't just about memorizing formulas and equations. It's about understanding the amazing ways in which matter interacts and transforms, and using that knowledge to make a difference in the world.
So to our listeners, I leave you with this. The next time you see something rusting, or eat a piece of fruit, or just take a breath, take a moment to appreciate the incredible invisible world of chemistry that's making it all possible. And until next time, keep exploring, keep asking questions, and never stop learning.